Today we're going to do scalar equations of lines in a plane. So we're going to look at the the last couple of days we've been looking at different forms of the equation. We've looked at parametric and general and vector and all those sort of stuff. We even looked at scalar equation, but today we're going to look more closely at the scalar equation of line. And before we do that though, I want to remind you of something that I briefly talked about a couple of units ago, something called the normal. And a normal vector to a line is a vector n which is perpendicular to that line. So on my diagram here, you see I've got line L, the blue line, and I've defined vector n as the normal, and it's perpendicular to this line. Now, since it's perpendicular, there's actually tons of different possible ends. I could move this up and down, and those would all be normals. This would be a normal going the opposite direction. And of course, any scalar multiple of the normal would also be perpendicular. There's one, there's one. You know, there's tons of different normals there. But of course, regardless if you slide it up or down, you're still going to have the same vector. If you go in the opposite direction, it's the same vector just with negatives. And any scalar multiple would also be the same vector. So the normal can be defined on a certain one. It's either the normal that I was given there, or any scalar multiple of that normal will also be one that's perpendicular to the line. So we're going to use this normal idea to answer some more questions about scalar equations. So let's look at our first example. We're going to treat this like a question just from the last couple of days, very similar to it. Develop a scalar equation of the line through the point 5, -1 with normal n, which is 3, 4. So before we would have asked you this exact same question, but probably would have given you something like, you know, a point and a direction vector, or maybe a point and a line. So you'd have to figure out the direction vector and say it was parallel. Today, instead, I'm going to give you a normal, which is no big deal. So our goal then is to find the equation of this blue line. And what we're given is this red vector, this normal of 3, 4. So since the normal is a perpendicular vector, I can go off and figure out what the actual direction vector must be. So the direction vector, the blue line, must be perpendicular to this. So I'm going to call the direction vector 4, -3. And I do this by remembering my little shortcut of finding perpendicular vectors. Remember, you take the two x and y's, you switch it, and you make one of them negative. So I took the 3 and 4, switched them, and made the 3 negative. Of course, I could have chosen the direction vector of -4, 3. That would still work. So now I know the direction vector, and I know one of the points on the line, and I don't need to graph it on the picture. I just know where the point is. And that's enough to get the information. Now, if you recall, when we found the scalar equation, we had to find the symmetric first. So first, find the symmetric. So since I have the direction vector and a point, I can find the symmetric equation. So it's going to be x minus 5. Remember, it's the opposite of what you see there. It's a 5, so it becomes -5 over the x component of the direction vector, which in this case is 4, equals y minus -1, which is +1, over the y component, which is -3. So there's my symmetric equation of the blue line. But what I want is the scalar equation. So I'm going to use this to get the scalar equation. So if you recall, we take the -3 and multiply it up, and the 4 and multiply it up. So multiplying the -3 gets me this. Rainbow. And then if you recall, this scalar equation puts everything on one side and a 0 on the other side. So I'll have minus 3x minus 4y, and then bring this across, and it'll be plus 11 when I subtract the 4. And of course, the scalar equation is just like standard form in that we can't have an x that's negative. So we're going to multiply everything by -1. So that was just multiply by -1 to put it in standard form. And we have our scalar equation of the line. So really, you probably could have answered this the last couple of days because it's very similar to the questions that we've done already. But the unique part is this idea of the normal. And if you stop and pay attention to our answer, we actually see something pretty interesting. If you look here, the coefficients on the x and y, the coefficients are 3 and 4. Well, those numbers should sound familiar because those are the numbers of the normal. So it turns out that that's always the case, that the coefficients on x and y are the same as the normals of the line. So the question is, can I maybe answer this a little bit easier? Well, first let's write a conclusion of what we just discovered. So just these are the numbers in the normal. And it turns out those are true all the time. So if we generalize this, then we can come up with this statement. A scalar equation of the line through the point P, and it could be P1 or P, it doesn't matter, with an x and a y, with a given normal, and in this case the normal is n1 and n2, is this. So what you do is you take the x component of the normal and it becomes the coefficient on x. The y component of the normal becomes the coefficient on y, and then plus some number at the end, which we'll figure out how to do. So I'll give you a second to look at that, or to copy that down. So given the fact that the normal then becomes the coefficients on the scalar equation, maybe I can answer this question a lot easier. Maybe I can answer it a lot quicker. So we're going to redo example 1. So if we remember, from example 1, the normal was 3, 4. And the given point was 5, -1. So now that I know that the coefficients on my scalar equation are 3, 4, I can write that right away. So that's going to be 3x plus 4y plus something equals 0. Then all that remains is trying to figure out what that something is. Well, just like in what we've done several times, we're going to sub in our point, because our point is on the line, so it satisfies the equation. So then what we'll do is just sub it in this point. So it'll be 3 times 5 plus 4 times -1 plus c equals 0. That's 15 minus 4 plus c equals 0. So c equals -11. And therefore our equation is 3x plus 4y minus 11 equals 0. And that is the same as the equation we got the other time. So of course this process should be a lot easier and quicker to find the scalar equation of a line given the normal.